All right, let's talk chemistry. Today, we're going to take a closer look at a fundamental rule you almost definitely learned in school. It's been the go-to for over a century for predicting how chemical reactions work. But what if I told you that rule might actually be holding you back?
Seriously, just think about that for a second. What if one of those core principles you had to memorize, a rule taught for generations, was actually kind of flawed? And in some pretty important cases, just plain wrong.
So, the rule I'm talking about is, of course, Le Chatelier's principle. You know the one. It says if you disturb a system at equilibrium, it's going to shift to counteract that change. Sounds pretty straightforward, doesn't it? Well, as we're about to see, that simplicity, that's its biggest problem.
Yeah, the idea is basically that chemistry is all about pushing back. You add heat, the system shifts to cool down. You crank up the pressure, it shifts to reduce it. It feels intuitive, right? But maybe it's a little too simple.
And listen, this isn't some hot new take. People have been questioning this for a long time. Way back in 1984, chemists were publishing articles asking if this principle was even useful anymore. The doubts have been around for decades.
And this isn't just some philosophical debate. It has real-world consequences. Check this out. In a study, 109 chemistry teachers in Nanjing were given a tricky equilibrium problem. When they tried to use Le Chatelier's principle to solve it, only one of them got it right. One. That's an unbelievable 99% failure rate.
So what is going on here? Where does it all fall apart? Well, the principle just can't handle it when things get messy. As soon as multiple factors start changing at the same time, like when a change in temperature also affects the pressure, the whole counteract the change idea can lead you to the exact wrong answer.
So, if Le Chatelier's principle is so unreliable, what are we supposed to do? Well, the good news is there's a much better way. A clearer, simpler, and way more accurate set of rules that will get you the right prediction every single time.
Let me introduce you to the Van't Hoff rules. Think of this as your new toolkit. Instead of that vague counteract idea, you get 4 crystal clear instructions. Temperature goes up, it shifts in the direction that absorbs heat, the endothermic one. Pressure goes up, it shifts to the side with fewer gas molecules. See? No guesswork, just a straightforward set of if this, then that rules.
Now here's a really important distinction to make. At this level, these rules are incredible predictors. They are your secret weapon for figuring out what is going to happen. The deeper why, well, that gets into stuff like equilibrium constants, which is a whole other conversation. But for making the right call, this toolkit is all you need.
Okay, enough with the theory. The best way to really understand how powerful this new toolkit is to actually use it. So let's put these rules to the test with a couple of real-world chemical reactions.
First up, let's look at how we make methanol. This is a huge industrial process happening in giant chemical plants all over the world. And the key thing to know here is that the forward reaction, the one that makes the methanol, is exothermic. It releases heat.
So here's a question for you. Using our new Van't Hoff's rules, what do you think would happen if we wanted to get more methanol? If we cooled the whole system down, would we get more of our product or less?
The yield goes up. It's a perfect application of our new toolkit. Rule number 2 says that decreasing the temperature will always shift the equilibrium in the exothermic direction. And since making methanol is the exothermic direction, cooling things down gives us more of what we want. Simple as that.
Okay, let's try another classic experiment. Inside this syringe, we've got a mix of 2 different gases that are in equilibrium with each other. We've got nitrogen dioxide, which is that brownish gas, and dinitrogen tetroxide, which is totally colorless. They're just constantly turning back and forth into one another.
So imagine we grab that plunger and pull it out. That increases the volume inside, which means the pressure drops. Based on our rules, what's going to happen to the color of the gas inside that syringe?
It gets darker brown. Now what's really cool is that for a split second, it'll get paler because the gas is just spread out more. But then, the equilibrium kicks in. Rule number 4 tells us that when pressure drops, the reaction shifts to the side with more moles of gas. In this case, that means making more of the brown NO2. So the mixture's final color gets darker.
Now, this toolkit is fantastic. It really is. But it's not magic. And like any tool, it's really important to know where its limits are, especially when things start to get a little more complicated.
Let's go back to that problem that stumped all those chemistry teachers. Here's why it was so tricky. The problem involved 2 changes at once. First, they added more of a reactant, which should push the reaction to the right. But the problem also said the pressure had to stay constant, which meant the volume had to get bigger.
and a bigger volume favors the side with more gas molecules, which was on the left. You get two opposite effects fighting each other, and without doing the actual math, you have no way of knowing which one wins.
And this isn't just some made-up exam question. Chemists in the real world deal with this kind of balancing act constantly. Look at the Haber process for making ammonia. The graph shows you get the best yield at really high pressure and low temperature. But a low temperature makes the reaction incredibly slow. So in a real factory, they run it hotter to speed it up, even though they know they're sacrificing some of their yield. It's all a big compromise.
So, what's the big takeaway here? It's that our simple rules are amazing when you're changing one thing at a time. But as soon as you have multiple competing factors pushing and pulling the reaction in different directions, you can't just guess the outcome. You need more data to figure it out.
All right, so let's wrap all this up and make sure your new, upgraded chemistry toolkit is ready to go.
So why should you care about any of this? Because switching to this Van't Hoff toolkit gives you a simpler, more direct path to the right answer. It helps you dodge all those common mistakes and traps that even experienced teachers fall into. It gives you a rock-solid foundation for understanding how chemistry really works, and it empowers you to predict what's going to happen with a lot more confidence.
And that kind of leaves us with one final, bigger question. We just took a long-accepted scientific rule, pulled it apart, and found a better model. It really makes you wonder, doesn't it? What other rules that we just accept as true, in science, in learning, in anything, might be ready for an upgrade? Thanks for tuning in.